imamo jedno, ja bih rekao, posebno predavanje u smislu tematike. Mislim da nismo još imali ovako clash dva jaka zvučna imena poput quantum computinga i machine learninga. Dolazi nam Puljak sa CERN-a. Ona inače je bila na FER-u, computer science je pozadina. Danas je u stvari zadnja godina doktorata, je li tako? I reći će nam nešto i dublje po pitanju tematike what the PHOS is QML. Inače, za vas koji ste tu prvi put, ovo je jednomjesečno okupljanje ljudi koji se bave machine learningom i oni koji se interesiraju za to područje. Cilj je i networking, osim dijeljenja znanja, tako da eto, pozivam vas i da ostanete nakon uz šank i da postavite pokoje pitanje Emi, odnosno Ema, zamolim vas da bude pitanje za vrijeme predavanja.
Da, uglavnom, ja ću, ili možete me prekinuti u bilo kojem trenutku, ili ću ja pitat nakon nekoliko slajdova ima pitanja. Jer ako ću do kraja ići, onda će biti previše pitanja do kraja. Možda,
Eto, da ne družimo, može vam pljesak za Emu. Ema, izvolite.
Hvala. I pričat ću na engleski, jer ne znam, pričam hrvatski o ovome. Okay, so since he gave an intro, I will just go on. So first I will introduce a bit what is a quantum computer, just to understand how quantum computer works. So first of all, you have a quantum version of a bit. Later I will explain what's a qubit. Then you incorporate it in some kind of quantum processor, and this is a 7-qubit quantum processor where actually you can see in the hardware the qubits. Here there are 7 qubits because they are implemented with superconducting circuits. And then you incorporate this into a quantum computer. So now in order to understand how the quantum computers work... sorry. Možete li me čuti? Dobro. Znači, ne treba mi mikrofon. Okay. So in order to understand how quantum computers work, you need to know three main characteristics of quantum mechanics, which is the superposition, entanglement, and interference. So first one is superposition, and through superposition I will explain what's a qubit. So in classical computing, you have bits, so you can decide either to take 0 or 1, so you need to decide one of each state to take. But a qubit can be in a linear combination of these two states, so there exists a probability of being in state 0 and a probability of being in state 1, or in more simple words, it can be in these both states at the same time. And this actually is very important for this parallel computation in quantum computers. And this is how you visualize it with this block sphere and this vector from the center of the sphere. It's important to say that this qubit can be in these two states at the same time before you measure it. When you measure it, it collapses to be a classical system. So for example, in this case, 70% of the time will be in 0 and 30% in 1. And this says, you can see that this measurement process is actually probabilistic. So the whole theory behind the quantum computation is probabilistic theory. After this, we can see it as a coin toss example, where the superposition would be spinning in both directions at the same time. So after this, we have entanglement. You can entangle or connect 2 or more quantum systems, and then they would be in some kind of special correlation. And then, for example, 2 of them can be in a superposition before the measurement, so they are in the both states at the same time. When you measure the first one and it takes the state 0, at the same time the second one will take state 1. And from this you can see this special correlation, and they are not physically bonded, so there is no any information being transferred between them. How you can entangle these qubits is, for example, from one particle decay, one particle that decays from one particle. These 2 particles who are decaying from the first one are entangled by the origin. So this can be an example of entanglement. And when you entangle more systems, you can increase the computing power of a quantum computer. And we can see this from this graph, where when you connect two qubits, you can express this with 512 bits of classical information. When you connect 10 qubits, you can express it with 16 kilobytes. And when you connect 280 qubits, you cannot express it with classical information because you would need as much bits as there are like atoms in the known universe. And then with this, you can see how exponentially information grows in quantum computers. And the last one is interference. So since qubits are behaving like particles and waves, we can take this feature of a wave and we can add and subtract them. So this is called the destructive and constructive interference. For example, in some problems, you can add these. You can add the waves of the solution you want to achieve at the end. And after this theory, it's important to note. So actually, first of all, do you have any questions? Okay. So first of all, it's very important to note why today the development of quantum computing is very slow and what are the obstacles for that. Qubits are very sensitive systems, and any interaction with the environment makes them collapse to these classical systems. And actually, the whole area of research is called quantum errors, and they are trying to find a way on how to isolate these qubits into a control environment so they can be kept, so you can operate with them in a controlled way. One of the methods is, for example, the first chips would connect qubits linearly, and then the error would propagate sequentially. But now they are connecting them in these heavy hex structures and some kind of more smart structures where you would correct the errors in a better way and more efficiently. And this is okay. Sorry. And this is how it looks like today for IBM and Google. This is their computer, and it's based on superconducting qubits. So this is all in vacuum, and it's around 2 meters high. So from here to here, you are reaching almost absolute zero temperature, because to get superconducting characteristics, you need to reach absolute zero. And the quantum processor is actually here. So you need to lower the temperature from the top to bottom. There are many ways on how you can implement the qubits and how you can implement quantum computers. If you're interested, I can show the slide at the end of the whole presentation. Noisy intermediate scale quantum era, which actually says that all these quantum processors are operating with noisy qubits, meaning that they are not error corrected enough. And so they have limited capabilities. And today they are between ASICs and FPGAs. And all the quantum computing is going towards these general quantum processing units, where actually you will have arbitrary amount of qubits. You can do arbitrary operations, because now you are limited with which kind of operations you can do on them. Okay. Do you have any questions? Because now I'm finishing the quantum computing. Yes.
You mentioned that for entanglement and for interference, they are using quantum particles. What quantum particles are they using to form qubits?
Okay. I know how to answer, but I have a whole graph of how you can implement. I can show it at the end of the presentation. Yeah, there are like 6, 7 of, yeah, okay. Any other questions? Yes?
So is this quantum approach and quantum computing changing the nowadays hardware and how we think about programming, or is it in cope with this, or is it some totally new technology?
It's new in the sense of, okay, you had transistors. They were like you started from the large computers. You came to very, very small transistors. And now you came to like particles. So it's kind of going in the direction that you cannot, the transistors cannot be that small anymore. So they are trying to find another way to do that on particle level. Yes?
Is there any theoretical limit for how many qubits can basically entangle together? So is it unlimited?
No. Yeah. Yes, there is a limit, but I don't know which one. But there is a limit also. I don't know if I have slides later in the backup, but in all of these processors, these qubits are not, they are entangled, they are connected in a special way because you cannot connect them arbitrarily. You cannot say, aha, this first qubit is connected with the third one. You need to have a smart structure to do this because of also these error correcting codes. So you cannot entangle them how you want. Not yet. Yes?
Is quantum computing today, is it a problem specific or it's a general purpose
Okay.
usage?
Yes, I don't have this in this slide. But so this one is going towards the general purpose. This is called gate-based quantum computing because you are operating with gates, kind of in like a digital logic. But you have also problem-specific quantum computing, which is a whole new branch, which is called quantum adiabatic computing. They are using processors, which, for example, you have an optimization problem. You give this to this company who is producing these processors, and then they produce the processor for you, where you can have 5,000 qubits, but they are connected in a special way for your optimization problem. Yeah, yeah. But this is we are calling it a fake quantum computing, like, because yeah. Yes.
So to follow up on my question, so that means if you, for example, have a 400 qubit computer, because you cannot make, because you cannot connect them arbitrarily, you basically cannot make 400 qubit entangled states as a single 400 qubit entangled state. I mean,
Not yet. Yes, not yet. Okay, so this is like in practice how it looks like, but to look at it from the theoretical point of view, we can look on them as a kernel method. So in kernel methods, you have a kernel function, you project your data in some feature space. It's similar in quantum computing. You take input data, you project it on this Hilbert space, it's called, and then you can access your results via the measurement. And I will explain how is this done, just to have this as an idea. In an intersection of quantum computing and machine learning, there are 4 research areas that you can look into. First one is tensor networks. They are quantum-inspired classical methods that are analyzing classical data, can be used to simulate quantum systems. Then you can use classical data, for example, a handwritten digit. You can encode it into quantum state and then operate on it with quantum computer. Then, for example, you have some kind of quantum data, which is, for example, a molecule. You have a mathematical description of the energy of the molecule, and you can transfer this mathematical description into the quantum model and then simulate it classically. Or you have this, again, quantum data, a molecule, where actually it can be directly analyzed on a quantum computer. And today, I will actually just talk about these 2, tensor networks and the first one, because this one is maybe not too interesting for you. For you, I can say later. Okay. So what are tensor networks? So first of all, I hope all you know what's a tensor, but okay, I will just say it's like a multidimensional array of complex or real numbers. In tensor networks, this is the notation we are using. So a vector is a node with one leg, which is it's because it's one-dimensional. Matrix has 2 legs because it's 2-dimensional. So legs are kind of saying what is the rank of the tensor. And each of the legs can have its own dimension. So let's start, for example, with the weight tensor in a neural network. It's a very high-order tensor. And in neural networks, you are always trying to ask, okay, how we can use less parameters to keep the same performance. And how you can translate this to tensor networks is that you can take this big tensor, use sequential sequences of singular value decompositions and factorize it to a maximum 3-order tensor. And then this is called a tensor network. Also, this tensor network has less parameters than the big weight tensor. And this particular tensor network is called matrix product state. And the features of this matrix product state are bond dimension and the physical dimension. Bond dimension is actually mimicking this entanglement or correlation between 2 neighboring tensors. And actually, and the physical dimension is, for example, the dimension of your data encoding. I will show this in an example later, so it will be more clear. And actually, if you want to do any computation with a tensor network, you need to contract or sum through this dimension. And you actually, there is a whole part where you are calculating. You need to find the optimal contraction path, because this speeds up your algorithm or all your computation. If you look at it from the point of view of quantum physics, you can have a quantum state and then factorize it to, for example, a matrix product state, or a 3-tensor network, or a 2D tensor network, which is called projected entangled pair states. So you can factorize it in different tensor network structures depending on your problem and what you are searching for, and like what's the type of your data. So this is a theoretical intro. I will give like an example on NISQ classification. So you have an input image. You encode it into some kind of higher Hilbert space with, for example, this trigonometric function. And then you create a product state. Product state means that there is no connection, or there is no this bond dimension, because we are assuming in this case that there is no connection between neighboring pixels in the image. And then you contract it with the MPS, or matrix product state, which has this physical dimension is dimension 2, because your embedding dimension is 2. And then the bond dimension is like a hyperparameter in tensor networks. And then you output the class. So this last index has a dimension of classes, or how many classes you want. And this function is the similar function you use in neural networks. So I think this, and this is the paper, if somebody is interested. So does anyone have any questions on this? Okay. Okay.
If I just understood correctly, that basically means that you're entangling the entire feature vector as
Yes.
a single entangled state.
Yes. You are entangling these, sorry. This means that you are entangling the whole feature space. I need to repeat the question. Okay, so no, you are entangling, since this is a 1D, like a linear chain, it means that you are entangling neighboring pixels, or how you want to, you can entangle in zigzag, or like how you, which pixels from the image you choose to put there. So you are entangling neighboring ones. This is a 1D. So if you have a 2D, if you have, sorry, this one, if you have 2D, then you would, your data would be embedded in a different way.
Okay, but does that mean that the entire feature space results with a single entangled state, or you have multiple entangled states of smaller dimensions that act together in a classical way then?
Okay, I see your point, but wait. Okay, so I don't need to repeat. I can
Sure.
explain. Yeah. So no, this means that you would entangle. It will be clear later when I show the quantum model. Then it will be clear how this is entangled, because here only 2 of them are entangled. For example, if you want to entangle this one with this one, you would take one bond like this. But then this would not be a matrix product state. It would be a different kind of. But you can do that. Yeah. This means that, so all entanglement in qubits, because this can represent, one of these tensors can represent a qubit. It represents a qubit. So if it's all-to-all entanglement, you would do like all the connections. But it's not needed for this case of NIST classification. Yes?
So entanglement is not transitive. Like if one is entangled to 2,
No, no.
2 to 3, that doesn't mean one is entangled to 3.
Yes and no. Like, yes and no. Part of it. So if so, yeah. Okay. So your question was if the first one is entangled with the second one, does it mean that the first one is and the second one is entangled with the third? Does it mean that the first one is entangled with the third? Yes, it means, but not fully. Not fully. Yeah. Okay. Okay, yes.
Jesu li sva stanja međusobno kvantno spregnuta ili samo jedan
Aha.
do drugog?
Ne, u ovom, ok, samo ću odgovoriti. U ovom slučaju ne, u ovom slučaju su samo jedan do drugoga, ali dijelom je povezan prvi sa trećim ako je drugi povezan sa trećim, ali ne potpuno. Okay. Now just to give this is a very complex example, but just to give an example of a connection with tensor network and quantum models. So you have this matrix product state. You can create a quantum model. It's like an exact representation. It's translatable. In this case, it's approximation because you need because if this bond is 2, then it's exact. If this bond is higher than 2, then it's not exact. You can create some kind of better precision quantum model. It's not important. But then when you train a matrix product state on a classical computer, you achieve some kind of plateau. And then when you achieve this plateau, you can say, OK, I stopped training on a quantum computer. I can use this state as an input state of a quantum model, and then train it on a quantum hardware, and then you can achieve better results. This is what I do, kind of. OK. Okay, so now the next topic is about encoding classical data and analyze them with quantum models. So you have some kind of encoding. I will talk about the encodings later. Actually, it's very important to choose the right encoding because it can solve all your problem at the end. Then you do some kind of processing on this quantum model through these gates and operations. So this is called quantum circuit. So when I was saying quantum model, it's quantum circuit. And this can be used as a machine learning model class. So these generators, predictive models are these quantum circuits. And I will show examples later. Then you perform a measurement to get some kind of output. And since quantum mechanics is a complex probability theory, then you need to repeat this process infinite amount of times, if you can, to be sure that your quantum state collapsed with your measurement to desired output. So basically, this is similar to sampling process. And then you repeat it to gather statistics, and then you can train it with gradient-based methods. I will explain all the parts as it goes. So first of all, how to encode your data in this higher Hilbert space. So it depends on your data type and the problem you have. For example, if you have a discrete data, you would use basis encoding, which would encode your data into n orthogonal states. If you have continuous and real data, you can use angle encoding, and then you would encode it into some kind of angular rotations. And if you have complex and continuous data, you would encode it with amplitude encoding to be like, so your state would be amplitudes of these feature vectors. And actually, to store this amplitude encoding for 2 to the n features needs n qubits. So it needs less qubits than you have features. And there are many other ways to encode your data. These are just like 3 basic ones. And actually, this brings us to the characteristic of linearity in this higher Hilbert space. So you have some kind of vector of data. You encode it into Hilbert space. And then whatever you do with these quantum gates is just a linear transformation. So it's just a rotation of the state in this space. So you cannot change the distance between these 2 points in the space. It's just so all these linear transformations in the quantum computers are basically because of the laws of quantum mechanics. And later, when you perform the measurement, it's still linear because there exists this linear boundary between these end states, 1 and -1. OK, are there any questions on this? OK. Now, to give examples of predictive models. So you take you want to produce a label. The label needs to be deterministic, but since this is a probabilistic process, you need to first do some kind of data and do some kind of state preparation. You perform these gates. Some of these gates can be parameterized, so they are trainable. And then you produce a measurement. Actually, these brackets here are saying that you are searching for expected value of the measurement, which means that it's a statistics processing of the outputs. For example, we are searching here when is the less qubit in the state 1, and then you average it, you get this prediction label. This is just a simple example. And in the mathematical point of view, you have these feature vectors. At the beginning, you perform a series of matrix multiplications, and then you get the output. So it's actually, it's not simple, but it's simple in the sense of mathematics at the end. Then the next one is generative models. So in GANs, you can choose either the generator or discriminator to be a quantum model, depending on what kind of data output you want from both of them. There are many different ways how you can encode, but I found one paper who really describes it visually. So first of all, you have some kind of noise. You feed it to the generator. Then there are two options in the generator. So if you want a classical output, you would take, for example, T smaller quantum circuits, and each of them would generate a patch of the image, and then you would sum this into a total image, and this is a classical output that goes to the discriminator. Or you can take a bit bigger quantum circuit where you actually encode the batch of these states into the quantum circuit, and then this quantum circuit is just plugged to the discriminator, who is again quantum. So there is no classical data coming into the discriminator. And then this, with the sampled data from the real images, you pass it to the discriminator, which is classical or quantum, depending on the input that comes there. And then it says is it fake or real, and continues the training process. And this is from this paper here, if somebody is interested to read more. Is there any questions here? Da.
Kad se želi dobiti rezultat od kvantnog računala, da konkretiziramo, recimo broj 21 rastaviti na proste faktore.
Dobro.
U kojem obliku će kvantno računalo napisati rezultat? Odnosno, kako će ga prikazati?
Dobit će se jedan, dobit će se jedan output od tog jednog prolaza kroz algoritam, ali se to mora ponoviti onako 100.000 puta da se bude sigurno da je to na kraju determinist. Da, vjerojatno.
Jer to je kvantna mehanika.
Da. Ok. Okay. So just to show what are these quantum parametrized models, which are used, for example, here for these smaller or the big ones, because they can be trained. So these are called quantum neural networks, that I call them like that. They are parametrized quantum circuits. So the first actually state preparation of the quantum circuit doesn't have a representation in the neural network. It's just that you take amplitude of the feature vector, and then you plug it into the other parts of the quantum circuit. All the other parts are, these gates can be either parametrized or can be fixed. So some of them you can train. And then at the end, all these gates apply these linear transformations. And then at the end, you are measuring. And this measurement is again linear, but you can look at it as a nonlinear activation function of the neural network, because you are actually computing absolute value of the amplitudes of the states to get the final result. And more visual example is maybe this one. So for example, a neural network can have only one qubit. And actually, if you translate it for quantum neural network. If you translate it from the neural network, so number of neurons in the hidden layers can be number of these block repetitions of uploading data into the circuit. Or, for example, number of hidden layers can say, okay, I want to have this number of qubits in the quantum neural network. So there are many ways you can implement quantum neural networks. Are there any questions on this? Okay.
How do you train these networks? I mean, when you perform.
Yes, I will. Yeah, this is after. I think it's really after. Yes. Okay. So how do we train these quantum neural networks? So what means to train a quantum neural network? It means that you find a measurement that minimizes the cost function that depends on some kind of training data, and you use gradient-based optimization. Well, you can also use gradient-free, but gradient-based, I will explain. So your gradient is a partial derivative of some function that depends on some kind of parameters. And to get a partial derivative in a quantum computer, you can perform what's called a parameter shift rule. Actually, you are just running your algorithm twice, and then you are shifting the parameter by some microscopic shift, each of them, and then actually the partial derivative is at the end, these two measurements, they are added, and you get a partial derivative at the end. And actually, this parameter S, this parameter S here is hard-coded in the software. So each type of the gate has its own shift parameter in the software. And all this is actually in the engines of all the quantum computing softwares today. And this is possible to implement on quantum hardware. So another question is, can you do the quantum backpropagation? Which is basically you need to perform a forward pass, which is possible in quantum computing. You get some kind of measurement, but it's not possible to perform a backward pass because this means that you would need to store intermediate operations on the hardware, which is not possible because of quantum mechanics. Because of this, you cannot clone a quantum state. Also, quantum state collapses very fast into a classical state. And today there is very big work on this. They are trying to basically create a way how you can create a quantum memory. And with this quantum memory, then you can store. But this is, I don't even understand the whole thing myself. OK. And actually, why we are not using so much either the parameter shift rule, because the quantum hardware today has a lot of errors. So you would have a lot of noise in your in your landscape, optimization landscape. And today, this is the most common way on how to train the quantum neural networks, is that you process you process something on a quantum hardware, you get the output, the measurement, then with the classical backpropagation, you return it back to the quantum circuit, and then you train it. So it's kind of a hybrid process. And since I mentioned the optimization landscape, actually, is there any questions? Because I switch now to another thing. I'm looking at you because you answered. Okay. Okay. Yes.
What is the main benefit of using quantum computers for such operations compared to classical? Is there some computational complexity difference or something?
Yes. Well, I will answer that later because I'm talking about that later. Okay. Okay, so there is one problem when you optimize a quantum neural network. It's called bar and plateau problem. So when you increase the number of circuits in a quantum computer, you are actually, your optimization landscapes become very flat, and then your gradients are very small, and then you cannot train. So this is a big problem in all these areas, tensor networks, quantum circuits, and it's, I cannot tell you how to solve them because we don't know as well. So there is currently very big research. Actually, the biggest one is in Los Alamos laboratory, which is in US. And then since optimization is hybrid, you can use all the machine learning softwares to deal with automatic differentiation. Actually, the most popular one is JAX today, because it has this ahead-of-time compilation. So it's very cool. Everyone is using this now. And all the quantum computing softwares are compatible with JAX. And these are the quantum computing software. So this one is from the Canadian company that does photonic quantum computing. Qiskit is from IBM. CERN is from Google, which is awful. And then, yeah, Google is not that cool. They are good in research, but not in practical things. And Yao, or how is it called, is one of the Chinese big, one research group in China has this software in Julia. And Julia is very famous now also in this community. And OK, so how to make a sense out of all this? So you need to actually, we need to ask ourselves what we are searching with quantum machine learning, so, and how you can benchmark all of these problems. So there exists, this year, so all these are the leaders of, actually this girl is a leader in quantum. in quantum machine learning. They published a paper where they benchmarked the biggest models and the biggest paper in quantum machine learning, and they tried to break them. They tried to like say, okay, why did you use a quantum model and not a classical model? And actually, they discovered that in many cases, you don't need a quantum model. You can use a classical, because classical machine learning is already good enough. And then actually, they are asking themselves like, why? That we need to rethink the whole quantum machine learning. Everyone is searching like a quantum advantage. Everyone is searching like, okay, how we can be better than the classical, but maybe this is not the question. Maybe the question is to find another use case that the classical cannot do. And since there is a lot of influence from the industry, we are all trying to find practical use cases in quantum machine learning. So in order to do that, this is just steps of how you put a problem statement, you take a proof, you create a proof of concept of this quantum circuit. Then you see how it's scalable, what resources you need, and then actually all this problem needs to work in simulation, meaning that quantum simulation is that when you perform all this computation without these errors in software. And then when this works, you can think about putting it on hardware. And then when you put it on hardware, you need to make it hardware efficient. So this is very big process for you to achieve some kind of advantage at the end. And now to summarize the most important applications of quantum machine learning. So one of the main maybe applications is quantum machine learning and chemistry. So these are called quantum simulations, where you simulate these chemical compounds, molecules, to develop new medicine, new drugs, new materials, because actually today we don't have enough power in supercomputers to simulate this, so we need to think about some other hardware, which is more powerful. Then to improve quantum computing, so actually you can learn these error correcting codes, learn how to mitigate these errors, or how to compile these quantum circuits. Then these, you can generalize it with less data. So every time we train these quantum neural networks, we use, I don't know, 100 samples, which in neural network you will use million. So you need much less data to train them. And then they can be new optimization algorithms, maybe. Quantum sensing, you can learn about the dynamics of quantum systems. And this metrology is, I don't know, I found an example of metrology. Is because when you variationally learn error-correcting codes, you can apply this to metrology. And then classical data analysis, you can faster and in more parallel ways search through data, and then you can also, I don't know, figure out if there are new correlations in the data. And at the end, well, not at the end, but almost, what are we doing at CERN? So at CERN, actually, we are motivated by the fact that all the data is fundamentally quantum. So basically, the data is classical because we read them out, but there is like quantum origin. So maybe we can leverage having a quantum algorithm instead of classical one. So this is the main motivation. And we are trying to search, actually, we are benchmarking the both. I cannot tell you. We did one work where it actually works with the quantum one better, but not always. OK, so open questions and concerns, and now I will say what's the truth about quantum machine learning. So actually, all these gates that you saw, they are called Pauli rotations. And actually, why we don't know why we use them and why we don't use another, some other rotations. In all these papers, people are saying, yes, we use this quantum circuit for this problem. But then when you ask them in a review, why did you use this circuit and not the other one, they don't know how to answer to you. They are saying, we saw it and it's common, but nobody knows why they use that one. So this is a very big question. Then how to properly benchmark them, because actually it would be better to use quantum data on these algorithms, but we do not understand fully what is quantum data for us or what quantum data we can use for these algorithms. Then before, is quantum advantage the right goal for quantum machine learning? Probably is not. Probably we need to find another way to think about quantum machine learning and, for example, not to use quantum circuits. There is other approaches that one can do. Then also, today it's cool to put quantum before everything and then say, it's better. No, it's not. Sometimes it's just overly complicated. For example, one of the examples is that how you can search in an unstructured database. It's the quantum algorithm actually brings a quadratic speed up on this, and this is one of the biggest that you can say for sure our quantum algorithm is better. But if your dimension is very small, then you don't need to use a quantum algorithm. Then you can just use a classical one. And that's it. These are all some kind of references, and from where I where I got inspired for the presentation. And this girl is working in this external company. I could be a spokesperson probably from the company because they have a best tutorial web page of this penny lane. And everything you want to learn from quantum machine learning, you can learn on this penny lane. I think I had where? This one. They have a very nice website. Everything is super visual, very nice explained. So if anyone is interested, you can go there. And I think that's it. So you can. So do you have any questions? Yes.
Vi ste spomenuli ključan problem kvantnih računala, a to je dekoherencija.
Jesam?
Onda se ja prečuo.
Jesam.
Valjda na ruskom nije bilo.
Pardon. Evo ga ovo.
Naime, hoću reći ovo, ne znam da li ste čuli da se upravo dekoherencija, odnosno pogreške kod kvantnih računala, dijelom rješavaju pomoću eniona.
Pomoću?
Enions.
Enions. A, da.
Oni su hipotetske
da, ali to ću, da.
Sad ću, ne da se sad hvalimo dvije rečenice. Prije 30 godina sam objavio rad enioni kao oni.
Imam ja slajdi o tom.
I počeo taj rad biti citiran, pazite. Onda sam se čudio zašto.
Evo ga.
Počeli su ga koristiti kod kvantnih računala. To radi naš Hrvoje Buljan na PMF-u u Zagrebu. Sa enionima pokušava naše rješenje stabilizacije i otklanjanja dekoherencije, znači otklanjanje pogrešaka. To je interesantno. A dobro, to vama kao informaciju dodatno dajem.
Pa da, imam ja slajdi o tome. Evo, samo malo. Da dođem do njega jer je on u backup. Aha, vi ste pitali, neko je pitao za one... Da, sad idem to tamo. Samo malo. Da, imam i to, da.
Mislim da to uopće nema.
Ne, topological, sad ću ja o svemu reći, samo sekund. Gdje je to? Evo ga. So, today, this IBM and Google have superconducting circuits. So, you are kind of implementing a qubit as a charge or a current or an energy state, which is 0 or 1. Then you can implement it with trapped ions, where you trap a photon into some trap. And then you have energy states, and these energy states 0 and 1 are 0 and 1 state of a qubit. Then you can implement it with these quantum dots, where the spin of a particle, which is some kind of characteristic of a particle, can be state of the qubit. You can implement it with photonic ones. These two temperatures are meaning that they don't require a specific temperature. They can operate on a room temperature. Photonic ones are kind of, you can use a polarization of the light or some other complex ways that I, to be honest, don't know how to explain right now. And this Canadian company is doing this. Then you can use a diamond and take one of these atoms out, leave a space, and put a nitrogen atom inside, and then this has some kind of structure of a qubit and can be even a Q-trit. So you can have a qubit which has 2 states. You can have a Q-trit which has 3 states, and you can have n, this quantum bit, can have n states. So there are like, and at the end, it's these topological particles that he was saying. Microsoft is doing these topological particles, but still they cannot prove that this is working on quantum processor. They had papers on this, but they can still not prove that this is working for a qubit or to be a processor in quantum computers. Yeah. And this is how this one I could not find how the processor looks like. Okay. Are there any other questions? Yes.
Format question. If I understood correctly, so basically since you still don't have a solution for quantum memory, you have to encode all the learned state in a classical way.
Yes.
In an external memory. And as you've shown in one of your earlier slides, that there is a lot of bits in a classical that to encode a single qubit. So basically that means that you still need a lot of classical memory for storing the weights that you then encode into an entangled state to run on a quantum hardware.
No, because you are collapsing the state in one of the states. So when you would represent all the states of superposition, you would need this many classical bits. But since at the end of the computation, you are collapsing your state in one classical bit, meaning that it will take one of the, so you just need one bit at the end.
But during the learning phase, that one single collapsed bit,
okay.
I mean a lot of them, then are used to update the weights, which are then during the training and later in the inference phase, re-encoded into a quantum state for in order to be run on a quantum hardware.
Yes, I understand.
That slide with the cycle.
This one.
Yeah.
Okay.
So in order to update the parameters, you need to collect all the collapsed states, so all the measured information from the quantum hardware, update the parameters, and then to run again through quantum hardware, you need to encode those parameters back into a quantum state in order to be usable on a quantum hardware. Did I get it correct?
Okay, I understand so you are thinking that I need this many qubits that are encoding in a classical way to update them. No. No, I just process the quantum algorithm. I get a classical information here, and then I put it back in a classical way. It's just a one bit of information that's updating the parameter in this quantum gate. It's like a matrix. It's like a unitary matrix. You can see it. And then this is like that you would update the weights in a tensor. You can look at it like that. Yes, but you don't need this much of information.
Yeah, but the quantum hardware is essentially stateless. I mean, you feed the updates. You feed the parameters and the input, and it does its magic. Then you perform the measurement. You either use it to update the parameters or for inference. But in general, in order to feed the inputs to the quantum hardware, you need to make a quantum state.
Yes.
With the methods that you showed
yes.
earlier.
Yes, but this is just you encode as you would encode one.
Yeah, but in order to encode, you need to have all that information stored in a classical way because you don't have any quantum memory.
Encoding process is classical process. I mean, you are starting from the classical process, the encoding. Yes, so you don't need to store any. The encoding process is deterministic. You will always do it's always the same process.
I'm just meaning, for example, if you have a 20 qubits,
okay.
You said that's like 300 gigabytes or something.
Okay.
Which means, if I understood correctly, that your parameters are in 300 gigabytes size.
Okay.
Am I correct or not?
Yes, but I don't know where you're going.
I'm just saying that.
Let's table it for later, maybe.
Yeah. Okay. Sorry.
Next question.
Yes. Any other question?
I think there was a question, and you mentioned this 6 or 7 slides to answer it later.
Yeah, I answered. It's okay. This one. Maybe just to show how. Okay, this is one of the quantum-centric supercomputer center in IBM, which has in the middle the quantum computer, and all the others are classical computers to communicate with the quantum. 1 second. Where is this thing? I don't have this slide probably here. Okay.
Okay, so next question.
And could you tell how do you manipulate qubits and different realizations of quantum computers?
No.
No. One at least?
Okay, with superconducting, I guess it's with current, or as you would. Yeah, it's electric. Yeah, I had in a previous presentation, I had a whole slide with this, like you can see them, but with the other ones, I don't know, because actually I mostly I mostly do tensor networks, which is like a simulation. And then now I'm doing this translation to the quantum circuits. Before I was running something on the quantum circuits, but I am not concerned on a hardware level, how is it operating. Yeah.
Because they're like really delicate operations. Like
Yes, like collapsing time is in nanoseconds, like very small, yeah.
Any more questions?
Možda neki algoritam da čujemo ili Shorov ili Graberov i ovako.
A nisam to imala ako. Ne.
Mislim, Shorov je interesantan,
Je.
jer on radi čuda čudesa.
Je.
Razbije mjesto 1000 godina za sekundu.
Je.
Okay,